When we're integrating, we have some strategies that we can apply. Our primary one is power rule when we deal with any kind of polynomial or any power function. We also have these common integrals. The integral of sine is negative cos. Integral of cos is sine. Integral of secant squared is tan. Integral of e is e. And for the a to the x, we just have the same a to the x, but we have to account for the non-base e. And 1 over x is going to integrate to log. Now, some integrals do not fall into the categories above or the power rule. So what do? So example is this one here. We have 2x over x squared plus 1. We cannot isolate the powers on x. This is a divide function, so we have these combined with division, and we have no way to kind of accommodate that. So we need some other strategy to deal with integrals that don't fall into standard categories. So we're going to look at the chain rule to start. And the reason why we're going to look at the chain rule is just we're going to use this idea that integration and differentiation are opposite operations. So if something happens with differentiation, then we can say that we can integrate its opposite. So here, for example, if we take a look at these ones above, most of us don't remember necessarily secant squared, but we can get the secant squared integral by knowing that tan differentiates to secant squared. So we're going to kind of take the same approach. We're going to look at the chain rule first. So if I take an embedded function like this, and I go in this direction, okay, so I'm going to go in that direction. I'm going to differentiate going from right to left. And if I differentiate that embedded function, I get the outside derivative here. I get this outside derivative, and then I have to attach a chain onto that, okay, the g prime. So that's the derivative. So if that is in fact the derivative of an embedded function, if I integrate that function, I should be able to go from right to left. So it's from left to right. Okay, so differentiating is right to left, integrating is left to right. So this is our expression that we're going to integrate, this one right here. Now, how do we know when we have an expression like that? Because this looks fairly complicated. So how do we know when we have an expression like that? Well, what we do is we're just going to make this a little bit easier to look at, and we're going to substitute u for g, the inside function, and what we end up getting is f of the embedded function u, and then we get our derivative of, which is du by dx, and then we have our times dx. And what ends up happening is if we can generate this du by dx, we can then actually algebraically simplify this and just get rid of those dx's, and we end up with f prime of u, and we end up with a du. And what that does then is it allows us to integrate whatever integral we have here in terms of a u variable or a simplified variable. Okay, so this looks a bit complicated, so we really need to see what this looks like in action.